Welcome. I think it's finally time we start talking about a project that I've been working on for the last couple of months. For my Masters, I've been developing this. It's an interactive lighting system for an immersive audiovisual installation. Obviously, it's not installation ready quite yet. This is just a prototype, but the systems are working, the code is up and running. So before I get started on the final build, I just kind of wanted to run through what's going on, how it's all working, and where I plan to take it from here. Plus I kind of need to get something together for my deadlines, so no pressure. So the project is based around WS2812B individually addressable RGB LED strips, controlled by an Arduino microcontroller. Now, to save space, I actually ended up using an Arduino Nano in the final build rather than the Uno. They're pretty much the same thing, just with a considerable size difference. Interactivity comes from an array of 3 HC-SR04 ultrasonic ping sensors. These sensors work in much the same way as sonar, so by sending out a high frequency ping, the sensor can listen to the response as it bounces off nearby objects. We can then use the Arduino to measure the amount of time it takes for the ping to return to the sensor. This is known as a time of flight calculation. Now, because the speed of sound in air is a known and largely consistent value, we can use this information to calculate the distance between the sensor and an object that's placed in front of it, assuming it's within the sensor's operating range. So these sensors have a minimum distance of 2 centimeters and a maximum distance of 4 meters. I averaged and smoothed the data from these 3 sensors to create a useful stream of data that could be used for some sort of control. I experimented with using it to control brightness, which worked but wasn't as effective as I was hoping it was going to be. So I decided instead to use the distance data to blend between colour palettes, which I think creates a far more obvious and impactful change. Don't worry, I'll talk more about the code that makes this work later in the video. In the final installation, as well as interacting with the light, I plan to bring the audience into the audio side of things in real time, essentially making them part of the artwork or the tool used to create it. A lavalier mic is hidden inside the light, transmitting to an audio processing brain built in Max MSP. I'll be going into more detail about the devices specific to this project shortly, but if you want to go into more detail about the devices not mentioned, follow this link to some of my previous videos. Oh, and just to make things a little bit more complicated, I'm using a Node MCU, which is a different kind of microcontroller, similar to an Arduino, but with a Wi-Fi chip built in, to send average distance data as an 8-bit integer with UDP over Wi-Fi to Max to eventually modulate something. Oh, and Max is talking back as well, so it's sending number values to the light to tell it which pre-programmed animation to play. So everything's talking to everything and it's all connected. But now, even though I planned this kind of project a few times, I've never actually made something like this, particularly not the actual physical making of a thing. So for anyone who knows how to make things, or does woodwork, or knows how to use a soldering iron, I apologise for what you're about to see. It's not bad, but it definitely embraces the jank. So the first step was to build the larger infrastructure, by which I mean the main body of the light, adding the LEDs, running the power and data lines, and building a base and enclosure for everything to sit on and to hide the circuit board that will eventually control everything. A fair amount of time was given to considering what material to use as the main structure. It had to be sturdy, diffuse light well, be cost effective and easy to work with. PVC piping ended up being the obvious choice, as at roughly £1 per metre, it's very cost effective and easy to cut and glue together with solvent cement. Not only that, but the way that light behaves with the material is really interesting. It diffuses light really smoothly and ends up looking as though the colours are being projected onto rather than emitting from the light. This does mean that it's less effective in a well-lit environment. However, given that this is for an installation in a dark room, that shouldn't be an issue. Using strong solvent cement that I definitely recommend using in a better ventilated space than I did, I glued 3 half-metre length pieces of piping together and taped them together until the cement had set and formed a strong bond. Definitely make sure you leave enough time for the cement to fully set. I got a little bit excited and messed this up. It's basic, but be warned. Once the cement has set, the tape can be removed to reveal a solid structure ready for LEDs. Yes, it's a different day. Continuity is an abstract concept here. Sorry. Once trimmed to size, installing the LED strips was pretty simple. These strips come with a layer of adhesive on the back. So all I had to do was remove the protective film and carefully apply 3 LED strips to 3 lengths of strip wood. I then soldered 5V ground and data lines to the input end of each strip to power and control the LEDs, before hot gluing into place inside the PVC pipe. 5V and ground lines were soldered to the output ends to pass power to the sensors. Yellow and green data lines also run through the light to pass serial data from the sensor array at the top of the light to the Arduino Nano in the base. The base is just a simple plywood box held together with wood glue and built large enough to house the Arduino, the Node MCU and a small power supply board. The PVC pipe structure is held in place by an obscene amount of hot glue. I plan to make the base slightly larger for the final build to provide more stability and to accommodate battery power and therefore wireless operation. With the light built, we can turn our attention to the circuitry. Throughout the build process, I built a few prototype control circuits to test various functions as the project progressed. My approach was to build a circuit to get the lights up and running, and then add the sensor and communication functionality on top of that. This is the circuit as it stands for the Arduino breakout board. The Arduino is receiving 5V power through the voltage in pin from a small power supply, with the ground returning to the same power supply. It's important to note here that when connected, the Arduino and Node MCU must share a common ground in order for the timing of the serial messages between the two boards to remain consistent. This is one reason for using an external power supply rather than powering everything from the Arduino's internal 5V rail. It also allows me to power both microcontrollers from a single 9V DC main supply. Power is supplied to the LED strips through the 5V output and ground pins on the Arduino, while data is fed from digital pin 2. Each of these lines is split in parallel to each of the 3 LED strips, allowing them to receive power and data at the same time and remain in sync. Digital pins 3 and 4 are used as serial receive and transmit pins for communication between the Arduino and the Node MCU. This works pretty well, however, because I'm using the Arduino software serial functionality to reassign these pins as serial I/O, I am noticing a small amount of interrupt that's affecting how smooth the code runs. It's subtle, but it's noticeable, so I'm currently exploring a couple of different approaches that will hopefully fix the issue. Finally, digital pins 5, 7 and 9 output to the trigger pins on the sensors, while their even counterparts 6, 8 and 10 handle the incoming echo messages. As I said previously, power is provided to the sensors from the Arduino's 5V and ground pins via the 5V and ground connectors on the top end of the LED strip. Here's the circuit diagram in full. Hopefully this gives you a somewhat clear idea of what I've got going on. Now, I've already touched on how the information from the proximity sensor is collected and passed to create a smooth stream of data. The time of flight measurement from each sensor is sent to the Arduino, where it is averaged. That average value is then smoothed using a simple moving average of the last 20 recorded values. Now, in the code, I chose only to include sensors whose value were within a certain threshold in this calculation, as I noticed that when one sensor's value was considerably larger than the others, it skewed the average and reduced the effect the other sensors had on the light. The output of this calculation is a float number between 0 and 1, assigned to the variable prox modulation. This is the number that I use later in the code to control blending between colour palettes. Now, as far as I can tell, The Arduino will only send integers over serial communication. It's unable to send floats. So I have to convert to an 8-bit integer, that is a number between 0 and 255, in order to send to max via the node MCU. To control the LEDs, I'm using the FastLED library for Arduino, which provides simple and efficient control over color and animation on the individually addressable LEDs that I'm using. Now, an extensive tutorial on the use of FastLED is far beyond the scope of this video, and I'll just be giving you a brief overview of how I've used it. However, I highly recommend Scott Marley's tutorial series, which I'll link below for anyone who's looking to learn more. One of the most useful and powerful functions of FastLED is the ability to use color ranges and gradient blending to define color palettes. At the start of our code, we define how many LEDs we are using. In this case, it's 31. And we can then use an 8-bit integer to define points along the strip, with 0 being the start of the strip and 255 the end. Colors are also defined using 8-bit integers to represent the intensity of red, green and blue values. Mixing and combining these color values allows for a huge amount of color variation with seemingly endless possibilities. Using these methods, we can tell FastLED to display defined colors at certain points along the strip. The program will then interpolate color values between those 2 points to create a smooth gradient blend. 5 color palettes are defined at the start of the code, along with the variables used to control which palette is currently being displayed. In the main loop, I'm using a custom function called palette blending, which uses the which palette variable to switch between palettes. Using if statements and the prox modulation variable, the function increases or decreases the value of the which palette variable based on the range that prox modulation is currently sitting in. It then switches the target palette variable to define which palette to blend to next. Pattern blending was a slightly more challenging problem to solve. Simply switching between patterns was as easy as assigning each pattern to a number and switching between them. However, this created a hard cut between patterns rather than the smooth crossfade that I was looking for. To solve this problem, I actually ended up using a well-established technique from stage lighting, which is actually quite similar to DJing or VJing. I'm using 3 pattern buffers here, 2 source buffers and 1 overall output buffer to crossfade between them. So as an example, while source 1 is playing the current pattern, we can queue up our next pattern on source 2 and use the output buffer to smoothly fade across. This process is controlled by an integer value sent from max that changes every time the scale changes on the spin drift device. More on this shortly. While the visual element of the installation is controlled by the Arduino, the sound side is built using the Max MSP visual coding platform. As I alluded to earlier, the Arduino and Max can talk to each other thanks to a Wi-Fi network and the User Datagram Protocol, or UDP, data transfer system. Essentially, Max and the Arduino are connected over Wi-Fi and send messages back and forth to modulate parameters in each other. The patch I'm using in Max is made up of a few devices that I built for a previous module submission for my degree. The approach I took to this project was to find a creative and interactive application for the generative tools that I had already built. As I said earlier, if you'd like to go into more detail about the specifics of these devices, you can follow a link in the description to a playlist of videos that explores them in much more detail than I have time for here. I would, however, like to give an overview of how this system is being used and some specific changes and devices that have been made for this project. Real-time audio capture is one of the main focuses of this system and is integral to incorporating the audience into the work. Using signal from the lavalier mic hidden inside the light, I'm recording real-time input into the sampling module and mixing it with pre-recorded field recordings and effects. The level that the real-time input sits at in the mix is controlled by the proximity value received from the Arduino and is therefore synchronized with the light as it shifts between color palettes. This mix of real-time and pre-recorded elements is chopped, stretched, reversed, and generally messed with before being output to multiple parts of the patch to become a different element of the audio experience. The signal is fed through reverbs, delays, and distortion effects. It's fed back on itself as well as being fed through the spindrift device, which uses bandpass filters quantized to musical scales to pull out resonances in the material and build up harmonic and ambient musical elements. The scales shift at regular intervals to create harmonic variation. The data that controls this shift is also sent back to the Arduino to trigger pattern transitions, creating another obvious and tangible link between the two systems. The other core element of the patch is the spatial audio system. Using Urcam's SPAT5 library, outputs from various parts of the patch are encoded into a third-order ambisonic stream and shift in position over time. Spindrift is used to create a more general spatial bed, while more specific elements are moved around the space at various intervals. While the system has been designed for an installation on a specific 22.2 immersive audio system, the versatility of ambisonics mean that it can be decoded into pretty much any listening environment and any number of speakers, including for binaural listening on headphones. Incidentally, the audio that's been playing in the background of this entire video is a binaural rendering of this video being played back through the lavalier mic and therefore the patch as if it were the installation. Let's take a moment to listen, and if you're not already, I recommend putting on a pair of headphones to get the full effect. Having the microphone hidden inside the pipe rather than being exposed creates a really interesting texture that, admittedly, once it's been chopped up and manipulated, is quite subtle, but it's definitely there. All in, this has been a really fascinating learning and development process, and I'm really excited to keep you updated on what will undoubtedly be the not-so-final form for the upcoming installation. So subscribe to stay updated on that one, but until next time, it's been real and thanks for watching.